Hi, my name is Hans Matthias, and I'm going to demonstrate the Dirty Cow vulnerability. This is a vulnerability discovered by researcher Phil Oster in 2016. The vulnerability is present in Linux kernel versions 2x and up, and was patched in version 4.8.3. The vulnerability allows for a race condition to occur due to incorrect handling of a copy on write feature. This vulnerability can be exploited by local users to write to read-only memory locations, and thus gain escalated privileges on a system. Before looking at the exploit itself, we need to look at race conditions and copy on write. First, race conditions can occur in shared memory programs where access to shared memory is not properly synchronized. To explain it better, I'll try to give an example. Let's say we have a multi-threaded program where two threads are tasked with reading the value of a variable and increment it by one. Let's say we are counting cars on a freeway. Thread A then reads the value in variable x, finds, say, the value 2, adds 1, and writes 3 back to the variable. Thread B will then read the value of x, find 3, add 1, and write 4 back to the variable. However, if this operation is not properly synchronized, what may happen is that thread A will read the value of variable x, find the value 2, but before thread A can add 1 and write 3 back to the variable, thread B reads variable x and finds the value 2. Then thread A writes 3 back to the variable, and thread B will also write 3 back to the variable. And we are now lost one count, or one car passing by. This is what is known as a race condition, and may also be referred to as a time of check to time of use bug. Copy on write, on the other hand, is a technique for managing memory resources. The idea is that if, say, two processes both wants to access the same, let's say, file, the file is then loaded into physical memory, and the memory management unit maps both processes' virtual memory to the same location in physical memory. This file can then be marked as copy on write, and what that means is that a copy of the file is maintained as a reference, not an actual copy, but a reference, until, let's say, this process wants to write changes to his copy. What happens then is that an actual copy is created in physical memory, and the memory management unit then remaps the process's virtual memory to the new private copy of the file. And you can now write changes to the file without affecting the other process. This way, memory resources are not spent on holding several instances of identical information, and rather kept available for other processes until changes are written to them, making two different sets of data. As we have now looked at both race conditions and copy on write, we can now look at how to exploit the Dirty Cow vulnerability. The code I'll be using is written by Kevin Du and is available on his GitHub page. As the exploit first runs, it opens our target file. In this case, we are targeting the etc password file in read-only mode. We are required to have read access to a file to be able to exploit it through the Dirty Cow bug. We then issue a system call called mmap, which is used to ask the kernel to create a private copy in memory of our target file. And the virtual memory is then mapped to our copy instead of the original file. We then search for the user we want to manipulate in the etc password file. In this case, we want to manipulate the user test cow with user ID 1001. And to exploit the race condition, we create two threads to race each other. The first thread tries to change the user ID of user test cow from 1001 to 0000, giving it root access. And these changes are written to proc self mem, which is a file representation of our virtual memory, which is now pointed to the copy. And since no data is written to the original file, but only our copy, we have read and write access to the memory. The second thread is used to issue a second system call called madvice, which is used to advise the kernel on how to do memory management. In this case, we use it with a value of don't need, which tells the kernel that we don't expect to use this private copy anymore. It can be discarded, and the memory management unit can map our virtual memory back to the original file. We now have three key actions taking place. First, we create a private copy and change the mapping of our virtual memory to the copy of the etc password file. We then write changes to our virtual memory, which is now pointed at our copy. And we have read-write access. Third, we discard the copy and change the mapping of our virtual memory back to the original file in physical memory. As long as these actions take place in this order, no data is written to the original file and no escalation of privileges take place. The problem is that actions 1 and 2, performed by the first thread, are non-atomic, which means there's no synchronizations in place to ensure that actions 1 and 2 both take place before action 3. Our code exploits this by running the two threads in a loop. And at some point, there's some degree of randomness as to when, but at some point, action 3 will happen before action 2. What we have then is that we create a private copy, we change the mapping of our virtual memory to the new copy, we discard the new copy and change the mapping of our virtual memory back to the original file, and then write changes to our virtual memory, which is now pointed to the original file in the original physical memory space. Now that we know how our exploit works, we can perform the privilege escalation. As we can see, I'm logged in as a user test cow. I have read access only to the etc password file. And my user ID is 1001. So we can now run our exploit code. This doesn't take long to take effect, so we can just cancel it. For the changes to take effect, we now need to log out from the user and log back in. And we can see that our $sign here has changed to a hashtag. And my user ID is now 0 instead of 1001, which means I have root access. And I can run who am I? And I'm root. Thank you for watching my demonstration of the Dirty Cow vulnerability.